Hello out there. Thanks again for taking another look at another video today. This one will be on inverse functions. So we'll start today by defining what an inverse function really is and kind of going from there. Let f be any function. A set of ordered pairs would be a function, or anything that we know of as a function. We can create another set of ordered pairs by reversing the pairs in f. We'll call this new collection f inverse, and we're using the notation f to the negative 1 power, which means f inverse. Okay. In other words, if a comma b is on f, then b comma a is on f inverse. Okay. Start off here with our first f. We have 4 points. If I want to know what points would be on f inverse, we simply switch the x with the y. So our set would consist of 1, 0, 3, 1, negative 5, 2, and 7, 3. For G inverse, switching the points, we would get 0, 0, and 1, 1. Not much to switch there. Negative 1, 1 would go, sorry about that. Negative 1, 1 would go to 1, negative 1. 2, 4 would go to 4, 2. Negative 2, 4 would go to 4, negative 2. And then many more after that. All right, 3a. First, let's do the domain and range of this function. So the domain of f would be 0, 1, 2, and 3. The range would be 5. Let's go in numeric order here. Negative 6, negative 5, 5, and 6. Or the domains, all the x's, range, all the y's. All right, so what would inverse be? Inverse would be 5, 0, negative 5, 1, 6, 2, and negative 6, 3. So the domain of the inverse then would be 5, negative 5, 6, negative 6. In numeric order, negative 6, negative 5, 5, 6. And the range would be 0, 1, 2, and 3. That's interesting. We'll come back to that later. All right, let G be defined by that function right there, this map function right here. The domain of G would be 0, 1, 2, 3, and 4. The range would be 1, 2, 6, 24 in numeric order. All right, so then G inverse would be defined by 1, 6, 2, 24. And 1, 4, 0, 2, 3. Okay, so 1 would go to 2 spots. 6 will go to 3. 2 will go to 2. And 24 would go to 4. Excuse me. Okay, so first of all, let's do the domain and range of, oh, I put this in the wrong spot. Sorry about that. That goes over there. Let's do the domain and range of our inverse function. So domain would be 1, 2, 6, and 24. The range would be 0, 1, 2, 3, and 4. Second of all, and probably more importantly here, what's something we should notice about this map? This map would not be a function. Okay, why not? Because of 1 right here going to 2 separate y's, 2 separate outputs. One input would have 2 separate outputs here. But again, look at what's happening here. So C says, what relationship do you observe between the domain and range of f and the domain and range of f inverse? Hopefully you realize here that the domain of the function is the range of the inverse and vice versa. So domain of f is the range of f inverse. And the range of f is the domain of f inverse. So basically they just switch. All right, slide 3, how to find inverses algebraically. So you need to pause the video here to copy this down. Feel free to do that. But first, we're going to rewrite the function as y equals. Then you're going to switch all the x's and y's. So anything from x becomes a y, anything from y becomes an x. Then you're going to solve that new function for y. And finally, rewrite your final answer as f inverse or g inverse or whatever we got there. All right, find the inverse of this function. First, let's write it as y equals 2x plus 9. Then every x becomes a y, every y becomes an x. And now we solve that for y by subtracting 9 and dividing by 2. And finally, our answer is going to be f inverse is x minus 9 over 2. So these two functions are inverses of each other. Number 5, rewrite it as y equals. Switch x and y. Solve for y by multiplying by 2, subtracting 5, and then dividing by negative 2, sorry. And our final answer would be g inverse of x equals negative x plus 5 halves, or negative x plus 5 over 2. Number 6, h of x. We write that as y equals. Switch x and y. Solve for y by squaring both sides. Adding 3. And dividing by 2. So h inverse of x is x squared plus 3 over 2. All right, graphing. We're not going to use our calculator here. We're just going to do it by hand. So f of x equals x cubed. If you want to use your calculator to help, you can do that. We should know what that looks like by now. Now solve for the inverse and graph that on the same coordinate plane. So y equals, switch x and y, solve for y. Final answer is x to the 1/3 or third root of x. Now if we were to plot that, it should look like this. Something we should notice, they're symmetrical. Not over the axis, but over this line right here. That line is y equals x. And that will always be true. Every inverse and every function and its inverse will reflect with a line y equals x. All right, let's graph d, negative x squared. Let's try that again. There we go. And now we're going to solve this. To get our inverse is root negative x. And if we were to plot that, well, technically it's plus or minus root negative x, we can only take x's that are negative or 0 to put into there. So if you put 0 in, you get 0 back. -1, you get root 1, so plus or minus 1. -4, you get plus or minus 2. And our graph would look something like this. Again, reflected over this line. I like that line to be dashed though, because it's not actually part of the graph. All right, letter E, x squared plus 4. Should look like that. And if we were to solve this for its inverse, first we switch x and y, subtract 4, take the square root, we get y equals plus or minus root x minus 4. Plus or minus root x minus 4. So we can only take numbers that are 4 or higher. If you put 4 in there, you get 0 back. Put 5 in, you get plus or minus 1 back. Put 8 in, and you get plus or minus 2 back, and our graph would look like this. And if we were to take this same line, y equals x, again, it should act as a mirror of symmetry between those two. So for a sentence or two describing the graphical relationship between the graphs of f and f prime, they should be mirrored or symmetric over the line y equals x. Look back at the open explanation, determine in which cases f prime was not a function or was a function. How can you look at the graph of function and determine if f inverse is a function or not? So this blue one is a function. It passes our vertical line test, right? This blue one is not. This blue one is not. So what we call this here is 1-to-1. What does that mean? It means that if f inverse is a function, then that original function must be 1-to-1. That means every input has exactly one output, and every output has exactly one input as well. Okay? So let's consider the following functions: f of f inverse and f inverse of f. All right, so if I give f inverse of these points here, 5, 0, -5, 1, 6, 2, and -6, 3. And we'll use this to answer the questions below. So the first question says, what is f of 2? F of 2 is 6. Then it says f of 2. F inverse of f of 2. F of 2 is 6, so it's f inverse of 6. What is f inverse of 6? 2. So f inverse of f of 2 is 2. All right. Next one, f of 0. F of 0 is 5. F inverse of f of 0, so that'd be f inverse of 5. F inverse of 5 is 0. F of 3 is -6. F inverse of f of 3 would be f inverse of -6. F inverse of -6 is 3. So we get back to the same output that we had for the input when we do f inverse of f of that input. Next one, if g of x equals x cubed, then g inverse, we already did this, would be third root of x, or x to the 1/3. G inverse of 8, so if we put 8 in here, we would get 2. G of g inverse of 8, so that'd be g of 2. G of 2 would be 8. All right, we can keep going like this. G inverse of negative 64 would be negative 4. G of negative 4 would be negative 64. G of that number, you might need a calculator for this one, as I do. We're going to take the cube root of that number here. So 2248091, cube root of that, we should get 131. And G inverse of that, so that'd be G of 131 would be our number 2248091. So our final takeaway here, if f inverse is a function, then f of f inverse is x, and f inverse of f is also x. So we can prove this. We can prove two functional inverses by showing that this is true, by using compositions. So if we can show that f of g of x is x, and vice versa, then they would be inverses of each other. So f of g of x would be 2 times cube root of x plus 1 over 2 cubed minus 1. Well, the cubed and the cube cancel out, so we're 2 times x plus 1 over 2 minus 1. 2 over 2 cancel out, so we're left with x plus 1 minus 1, or x. And now if we did g of f of x, so it's the cube root of 2x cubed minus 1 plus 1 over 2. So it's the cube root of 2x cubed minus 1 plus 1 cancels over 2. Cube root of x cubed, which is x. Hey, look at that. They both worked out to be x. Therefore, they're inverses. All right, last one here, B. I'll take a pause here as I have the bell ringing. All right, we'll start by doing f of g of x, and that would be 5 over x plus 2 minus 2. So that would be 5 over x plus 0, because 2 minus 2 is 0. So that's 5 times x over 5, which is x. And then g of f of x, so 5 over x minus 2 plus 2. That's equal to 5 times x minus 2 over 5 plus 2. 5 over 5 cancels, now it's x minus 2 plus 2, which is x. So we proved that if f of g of x is x and g of f of x is x, those two functions must be inverses of each other. All right, that'll do it for our look at inverse functions. Thanks as always for tuning in, and we'll see you again soon.